All right, well, thank you for joining for another calculus exploration here. We're going to be looking at differential equations. If you aren't familiar with them at all, basically what it boils down to is that we are looking at the idea that multiple variables are changing at the same time, hence the reason of differential variables, different variables changing. All right, so we're actually going to take a slightly different approach, though. This is not an introductory video into what differential equations are. This is more about how what the implications are on the integration side of things. A couple of side notes are just to kind of remember, that we have something called direct variation, and this is useful when you deal with differential equations. Direct variations, if you say y directly varies with respect to x, that means that you have y is equal to some constant k times x. If you say that y varies inversely with respect to x, that means you have y is equal to k over x, where x is in your denominator. So one of these is a linear relationship. This is more linear, all right, with a y-intercept of 0, and this is, of course, a rational function. And that's really the primary difference between these two situations. Is just another way of saying that the relationship between y and x is rational versus the relationship is linear. Both of them in both cases have a k value, which means there's some constant of variation in both situations, which is the connection between this and between equations and the differential equation part of that. One thing that we're going to look at is this idea of a particular solution. So let's just say that we're talking about y prime minus y equals 0. Now, if we want a particular solution or a general solution, we'll deal with both of those situations, we need to first figure out the general solution so we can find the particular solution. And what that means is, let's just say, let's ask the question, is, say, y equal to the square root of x a solution? Okay, and what I mean by that is, if we were to do the derivative of y equals the square root of x, would we get the equation that we have over here on the left? And this is a fairly straightforward situation here. We wouldn't. You can look at that very quickly and do that derivative. You'd end up with y prime being equal to 1/2 x to the negative 1/2. So this one would be pretty straightforward. This is not a solution. But the other thing we can do is what is the solution to this? So when we say the solution, in this case, we'd start with the general solution. We'd start by trying to what's called separate the variables. So we'd start by taking the left-hand side of this equation and try to separate the different components apart. So I'm going to do this. I'm going to have x, y prime is equal to y, and that means that y prime is equal to y over x. Now, when we're looking at this, there's still not a whole lot we can do with this, because if we were trying to integrate this as is, we could integrate y prime and we'd get y. But how do you integrate y over x? This is where the separation piece comes in. I'm going to rewrite y prime as dy over dx, and this is going to stay y over x on the right-hand side of that equation. Now, at that point, I can actually separate my variables. I can put my y with my dy, my x with the dx, and when I do that, I end up with 1 over y dy is equal to 1 over x dx. All right. Now, I can stick in my inequality signs here, and I end up with the integration of 1 over y dy, which gives me ln of y is equal to ln of x, and then still my plus c, because this is what we call our general solution. All right. Now, a number of us may be thinking, well, what else can we do with this? Is there anything else we can? Yeah, there's actually a lot of manipulations that we can do with this particular situation that we currently have. One of those is that this is not currently written as a function. So could we solve for y? Absolutely. So the thing you have to remember when you're rewriting a logarithm is that log base A of x is equal to b, however you want to write that. Logs equal exponents. So this b value is my exponent of my base right there, which is the a, right? So the way that we would convert this into an exponential notation as opposed to a logarithmic notation is this would be a to the b is equal to x. And maybe I should pick some other variable to make it a little bit clearer so we're not getting confused here. But here we're saying ln, the base there is an understood e. So this is e to the ln of x plus c is equal to y. And you could have written that the other direction with the other piece on the other side. And again, we can continue to write that because the addition of the powers here is the same thing as the multiplication of the bases with the same powers. So that means we got e to the ln times, ln of x, pardon me, times e to the c power equals y, which e to the c is some constant. So I can rewrite this as some constant of variation times e to the ln of x equals y. Now, there's still some other stuff with this that you can do. But one of the things I do want to point out is that we've essentially shown this to be a linear relationship or a direct proportionality. You say, well, how's that linear? Well, it has the behavior of a linear relationship with the constant of variation times your variable, essentially. All right, so this whole e to the ln of x piece is going to simplify for us. And we can think of it being a complete unit in of itself. But we still don't have an exact value. But one thing we could do is we could say, well, when x equals 1, y is equal to 0 or some other value. And then we'd plug in those values there, and it would tell us everything we would need to know about how the behavior between these two things interacts to give us a particular solution, right? So we take these values, we plug them in, and that would give us a particular solution. All right, and once we have the particular solution, then we would have, and there could be a lot of these, so we could say that in this instance, we'd have k is equal to e to the ln of 1 equals 0. Actually, I see a problem with that, so let's not let this be 0. Let's say this is, make a simple adjustment, just say this is 10. So ln of 0, ln of 1. And if you don't remember that, you can always grab a calculator. And if you're using a TI-84, right next to the number 4 is the button ln. So you just do ln of 1 and enter, and you see that that equals 0, right? So that means that you're talking about k times e to the 0 power equals 10. Well, is anything to the 0 power is 1, so that means that k is equal to 10. So the particular solution here is 10 e to the ln of x equals y. Now, is that all we can do with that? Well, I mean, isn't that enough? So at this point, what else is there to do? Well, what we found was a particular solution right here, okay? So what are the other pieces pardon me, well, this is the particular solution to that versus the general solution, which was right there. And the difference here is that in this instance, the constant variation, or that constant that is being added somewhere, is the same in either scenario. So the last question we want to answer, is there any more simplifying we can do to this? One way you can prove something to yourself that we can do more simplifying, and some of you may be looking at this as, can't we do something else here, is this idea of e to the ln of x. Well, grab your calculator and do e to the ln of 4. You'll find that's equal to 4, right? Do e to the ln of 5. You'll find that's equal to 5. Because what happens is when you have e and ln here, you have these two pieces, they actually cancel, and you're left with k times x equal to y. So you're actually dealing with a linear equation. So when you're thinking, well, this is not a linear relationship, and I said it is acting like a linear relationship, it's because it is. So this is actually 10x equal to y. So it has the same behavior. Now, as weird as that may seem, that we start off with, what did we start with here? That's what we started off with right there, right? Essentially, after we separated the variables and started rearranging pieces, and we end up with this. That may seem weird, but there is a very logical reason. We start dealing with these things, and we can start doing all sorts of interesting and neat things with population growth models and decay models and exponential formats. And what we can do here is show that we can rewrite these in terms of linear equations, which makes them significantly easier to work with. I hope you find these videos useful, and they help develop your understanding of calculus a little bit further. If you have additional questions, comments, or need additional explanations, please reach out and ask. Make comments or send me an email.